Okay, this is section 2. So this is the mean, the variance, and standard mean, variance, standard deviation, and mathematical expectation of these probability distributions that we looked at last section. So the mean to find these is simply by taking all of your x's times the probability of those x's. What the book doesn't do and what the formula doesn't show is, remember that sigma means you add up all of these. So what it kind of looks like is that you add up all of your x's and then you take them times your p sub x. What I want you just to keep in mind is understand that it's like this. You are going to add up all of the x's times the probability of those x's. You're going to do this first, and then you're going to add them all up. So you're going to do this for each x value, and then you're going to sum them up, okay? The variance is a little bit more complicated formula, but not so bad. Just for each x, you're going to take x squared, multiply it by the probability, and then add them all up. And then at the end, you're going to subtract the mean squared. So this little part is after the sum. Okay, it's after you do this. You'll see it when we work through a problem. Rounding rule for this. This is something, again, you're not doing on your tests, or most of you are actually. You're overall, you're doing a really good job of it. Usually on the quiz, many of you aren't doing a very good job, and by the test, you guys have all figured it out. So keep that up. But on the last test, there are still a few of you who aren't paying attention to the rounding rule, so just make sure you do that. Rounding rule for this stuff is one more decimal place than the outcome of x. So if all your x's are whole numbers, you would round to one decimal place. So here's an example. This is the probability distribution shown that represents the number of trips of 5 nights or more that American adults take per year. So it's basically, excuse me, how many times per year does an American take a vacation of 5 nights or more? So 6% of Americans never take a trip that's 5 nights or more. 70% only do 1 a year. 20% do 2 a year. 3% do 3 a year, and 1% do 4 a year. What's the average? On average, how many Americans, how many times per year does an American take a trip that's 5 nights or more? So remember in the formula right here, remember we're doing all of this stuff first. We're doing this for each x. So that's what we're doing. We're taking our x times the probability of x. 0 times 0.06. 1 times 0.7, 2 times 0.2, 3 times 0.03, and 4 times 0.01. Then, after we do all that, we're summing them. So we're adding them all up. And that comes out to be 1.2. So on average, an average American, 1.2 times per year, they go on a trip of 5 nights or more. A talk radio station has 4 telephone lines. The host is unable to talk or is talking to a person. The other callers are placed on hold. So I have four telephone lines. If for some reason the DJ is away from the desk and can't talk, or if they're talking to another person, the other callers are placed on hold. Okay. When all the lines are in use, others who are trying to call in get a busy signal. The probability that 0, 1, 2, 3, or 4 people will get through is shown in the distribution. So this is basically saying that 0 people will get through 0.18 times, 1 person will get through 0.34, and so on. we want to find the variance and the standard deviation. Now, in order to find the variance, you have to have the mean. So if we go back a formula, remember you have to have the mean. Remember your standard deviation. We should add that. Your standard deviation is just sigma. So it's just whatever this is, not squared. It's the square root of this. Okay. So let's find the mean first. We multiply all of these, add them all up. There's our mean. So now the variance. The variance is your x squared times p of x. Add all of those up, and then minus your mean squared. So think of it as we're doing really like this part first. Okay. 0 squared times 0.18, 1 squared times 0.34, 2 squared times 0.23, 3 squared times 0.21, and 4 squared times 0.04. I want you to do all that. Make sure that you're able to do this correctly. And then subtract the mean, which we found right there, squared. And you should get 1.2. And then the square root of that, right, all this is the square root of 1.2 is 1.1. And that's your standard deviation. So if that talk radio station has 4 telephone lines, if the host is unable to talk or is talking to another person, the other callers are placed on hold. So remember that. When all lines are in use, others who are trying to call get a busy signal. The question is, thinking of that, should the station have considered getting more phone lines? Okay. So do you think that 4 is enough, or are they too often going to have people, on hold? Well, they say no, 4 phone lines should be sufficient. And here's why. On average, what we figured out is there will be 1.6 people calling. Okay? On average, at any one time, you have 1.6 people. Our standard deviation was 1.1. So if you go our mean plus 2 standard deviations, okay, so that would be 1.6 plus 2 times 1.1 gives us 3.8, right? That's 2.2, 1.6 and 2.2 is 3.8. Now that's on the high side, right? Remember, this is your formula for outliers. 4 is an outlier. So if we ever get 4 people calling in at one time, that's an outlier. Not saying it'll never happen, but not very often. Okay. So their explanation is very few callers would get a busy signal, since at least 75% of the callers would either get through or be put on hold. And this is according to Chevy Chevs. Remember, 2 standard deviations with Chevy Chevs covers at least 75%. And I think that's even, that's at least, I think that would actually happen more often than not. Let me go back and correct myself. I was thinking the other formula, the interquartile range. This is not your formula for outliers. Sorry, that's coming up later. This was just checking out the high side for Chevy Chevs. Between obviously 0 and 3.8, you'd have 75% of the callers. So, sorry, correction, this was not your formula for outliers. That formula for outliers, I forgot, was this, plus or minus your 1.5 of your interquartile range. So that would be for an outlier, which we're not looking for right now. Expected value. This is what you're going to be doing for Wednesday with our carnival games. We want to figure out what's the expected value, or the expectation. And all expectation is Every time you play a game or every time something happens, what can you expect? What's the expected value if you play it long enough? That per turn, okay? Um, by definition, it's called the mean of the probability distribution, and it's simply found by doing this. It is the mean, okay? But what does that actually tell us? So here we go. We're going to set up a game. We have 1,000 tickets, okay? Um, out of those 1,000 tickets, we're selling them for $1 each. They could either win $100, $50, $25, or $10. Okay. After each prize drawing, the winning ticket is then returned to the pool of tickets. What is the expected value if you purchase 2 tickets? So we want to find what's our expected value per like every time you play it. Okay. So here we go. You can look at it 2 different ways. This is the first way you can look at it. Is how much do you gain? How much do you gain? You're buying 2 tickets at $2 a piece. Okay? You could win $98, right? So you buy 2 tickets, they do that drawing, and then they put the tickets back. You could win $48. You could win $23, or you could win $8. Where we get that from is these cash prizes minus the $2 you spent on 2 tickets. Okay. Or you could not win anything, and you could lose $2. What's the probability of doing that? Well, you have a 2 out of 1,000 chance of getting $98. Okay. The reason it's 2 out of 1,000, you think, well, you know, why can't I win the $100 ticket twice? It's because after each prize drawing, so after each time they, once they get that prize, that ticket goes back into the barrel full of tickets, right? So you could win $48, 2 out of 1,000. You could win $23, 2 out of 1,000. Or you could win $8, 2 out of 1,000. Everything else, think about that. That's 1,000 minus 8. 992. 992 times out of 1,000, you will lose $2. So we find the mean. We take 98 times 2 out of 1,000, 48 times 2 out of 1,000, 23 times 2 out of 1,000, 8 times 2 out of 1,000, and negative $2 times 992 out of 1,000. Do all of that math, all those calculations, and you get a value of negative $1.63. What does that $1.63 mean? That $1.63 means that every time you purchase 2 tickets, you can expect to lose $1.63. Okay, that's your expected value. Does it mean you'll actually lose $1.63? No. There's no possible way to lose exactly $1.63 because if you buy 2 tickets, that's $2. If you lose the $2. If you win, you could win 8, 23, 48, 98. The point is that the game will expect to win $1.63 per person that comes and buys 2 tickets. That's what they can expect to win. So let's say they run this game and they play this game. 10 people come. Okay, 10 people come and play this game this way. What should the owners of this expect to have made so far? Well, if each person is losing $1.63 and there are 10 people who have played that, that's negative 16.3. This is through the eyes of the player. Okay? If we were doing this through the eyes of the people running the booth, these would be negatives and this would be a positive because we're looking for, they would expect to lose $98. And everything would be flipped, and it would just be a positive $1.63 because that would be through the eyes of the person running the game. So back to this. After 10 rounds, they should expect the runners of this booth, they should expect to have about $16.30 in profit. Now we know it's not going to be exactly $16.30 because there's no cents involved. Like none of these games have cents. But that's roughly. Will they have exactly negative 16, or will they have exactly $16.30, or will they have exactly 16 or exactly 17? Probably not. There's a good chance they will, but they might be at 15, they might be at 18, they might be at 14, they might be at 20. Maybe somebody came and had a really hot streak, or maybe they've already given away this $98 prize. The point is that this is on average. So if you play this game, a million times, you're going to get closer to the real amount of number, the real value that you expect. Here's that alternate approach that I was talking about. Okay. What if we just look at the prizes? So you could gain $100, you could gain 50, you could gain 25, and you can gain 10. Or you could gain $0. You could gain $100, 2 out of 1,000, $50, 2 out of 1,000. The probabilities are the same. Or you could gain $0, 992 out of 1,000 times. So we add all those up, except we have this little red part here. You see that? Why are we taking away $2? The reason we're taking away $2 is because you could actually add one more thing here. You're going to lose $2 1,000 out of 1,000 times. Every single time you are going to lose $2 and then also possibly gain 0 or gain 10 or gain 25 or gain 50 or gain 100. So you can kind of look at it as two ways. These are the prizes and that's the opportunity. And you have to pay $2 to play. Where here, the previous one, we took that $2 into account already. So it's totally on how you look at it. But again, this is just saying you could win this, or you could win nothing. But every single time you have to pay $2. And you see we get the same answer.